Okay, this question initially asks for the molar solubility of magnesium hydroxide. So we'll write out the dissociation. And KSP. Alright, our ice table. The solid, as always, does not appear. We assume we don't have any of these initial ions. When S moles dissolve, we get S and 2S moles of magnesium and a hydroxide. Equilibrium is the initial plus the change. Note the squared is outside of the brackets because 2S represents the hydroxide ion concentration. So KSP is equal to S times 2S times 2S is 4S to the third. We want S. So if we initially solve for S to the third, you see that's KSP divided by 4. To get S, we take the third value, or the third root. And since KSP is given to us, we can pop that in there. And we find that S is 1.1187 times 10 to the minus 4, which if we have two sig figs, 1.1 times 10 to the minus 4 moles per liter. Alright, here we have a common ion, because we have a concentration initially of hydroxide. We can find that concentration by raising 10 to the minus POH. Since POH is going to be 14 minus pH, which in this case is 1.00, 10 to the minus 1. This equals 1.0 times, or just do 0.100. Okay, so otherwise the problem's solved the same way. And we need to take extra care setting up our equilibrium table, our ice table. While we don't have any magnesium, we have 0.10 molar hydroxide at the start. So we're going to gain S, we're going to gain 2S. So this is S, 0.1 plus 2S. Right, so that equals S and 0.10 plus 2S quantity squared. Now we're going to see if we can make the approximation that this S is insignificant here. So we multiply KSP times 1,000, and so it's going to be 5.6 times 10 to the minus 9, and 0.1 is much, much larger than KSP times 1,000. So our approximation is okay. So this is approximately equal to S times 0.1 squared. So we made the approximation that this S is insignificant compared to that concentration. So S is equal to KSP divided by 0.1 squared and our new solubility is 5.6 times 10 to the minus 10 moles per liter, which we see is much smaller in basic solution than in pure water. Okay, so we're done, but I wanted to point out that this makes perfect sense. Solubility of magnesium hydroxide, which of course is a basic salt, is lower in basic solution. pH of 13 certainly qualifies as basic solution than in pure water. Remember, this is a general result for basic salts. They're going to be less soluble in basic solution than pure water.